So a very good afternoon to all. I welcome you all on the behalf of Electronics and Communication Engineering Department, MIT University, Haryana. Today we have a talk on building the future challenges and opportunity in semiconductor research. And today our presenter is Ratul Kumar Barua. He is associate professor with the Tezpur University, Assam. He did his PhD from IIT Guwahati and postdoc from Purdue University, USA. He is the expertise in the semiconductor devices and VLSI. So he is among us. And thank you, sir. We welcome you on the behalf of our faculty member and HOD. Thank you all. Thank you, sir. Sir, you can, over to you, sir. You can start now, sir. Thank you, sir.
Okay, thank you so much, Dr. Neeraj. It's nice to be with you this afternoon. So I think students, around 25 students have joined. Let us start, and meanwhile students will join. Okay, so as you requested, the today's topic is kind of a very introductory topic. So I will speak on challenges and opportunities in semiconductor research. And this is mostly for undergraduate students, BTech students of ECE, electrical or instrumentation or related subjects. Okay, so I will speak on semiconductor research, its definition, its importance, then what are the challenges in semiconductor research, VLSI design flow, semiconductor devices, then junctionless transistors a bit, then how to improve the drain current in the junctionless transistors. And at the end, I will stop by saying what are the opportunities in semiconductor research in terms of job and higher studies. So as the slide says, so electronics has been used in everyday life in all applications. So we cannot think of a life without electronics products, starting from laptop, smartphone, defense, nuclear science, everywhere. So of late, people are being used electronics as flexible devices, then Internet of Things, then medical applications, etc., etc. Now, if we see the biggest companies in terms of revenue, the semiconductor companies, TSMC, Intel, Qualcomm, Broadcom, Micron, NVIDIA, Applied Materials. So all these companies either from US, Taiwan, or Netherlands. So none of these companies are from India, basically. So if we see the expectations from customers, while buying electronic gadgets, so people generally see performance. Performance means in terms of speed. Everybody wants a device with a very good speed, then very good battery life, then reliability of the device, durability of the device, then storage capacity, of course, value for money, then camera quality if someone is buying a smartphone, and etc., etc. Okay, so if you see the revenue of the semiconductor industry, so it is booming each year. So if we see, I have a data from 2019, it is $412 billion. Okay, and each year it is being increasing. And the main challenges are the fabrication automation. So Internet of Things, artificial intelligence, wireless communication plays a big role in the semiconductor industry. So as per the report, there are many, jobs in these areas. So industry still need lots of manpower in these areas. So main issue is we need high performance as well as low power at the same time. Then static power dissipation is an extremely important issue in addition to the dynamic power. So, earlier when the devices or the systems were bigger, then we gave more importance to the dynamic power dissipation. But with the device sizes being smaller and smaller every day, so we are more interested on static power dissipation. So another issue is rapid technological changes, global competition, compactness, reliability, cost, efficiency, fabrication complexity, which reducing the sizes of transistors. These are some of the concerns. Then to achieve this, to include more number of transistors in a single chip, the transistor sizes are being diminished each year. And this is what is called as transistor scaling. And transistor scaling has reached the physical, the physics limitation. Okay. So now let's start with the Gordon Moore's law. In 1965, Gordon Moore predicted that the number of transistors would be doubled in every 18 months. And that has been followed from 1970s, in 1971, in fact, to till 2021. So Gordon Moore's law is followed. Okay. Now, if you see in 1971, the size of the channel length of the transistor was 10 micrometer, and it has been reducing over the years. And in 2022, it is only 3 nanometer. Now, to give you an example, so this is the example of the companies who are working on different kinds of technologies. So if we had started with, for example, 180 nanometer technology, so you can see lots of companies are working in this technology 180. Now as the technology is diminishing, then 130 nanometer technology, some companies left, then 90, some left, then coming forward. And if we see for 10 nanometer technology onwards, only 3 companies are fabricating the devices: Samsung, TSMC, and Intel. So this is because the excessive cost of the foundry. Now to give you an example, to have the cost of a foundry for lower technology nodes, for example, 10 nanometer or so, so few tens of $billion is required. So only few companies like Samsung, TSMC, Intel can survive in this, cost region. Now, for example, when I say 10 nanometer channel length, I mean that if you see the figure on the left hand side, so I have 2 different types of lengths. One is called gate length and another is called channel length. So gate length is higher than the channel length. So channel length is equal to gate length minus twice into the diffusion length. The lengths, the extra lengths is called the diffusion length. Okay. So to give you an example, in 28 nanometer technology, for example, say, when we say 28 nanometer technology, the gate length is actually 28 nanometer. The actual channel length is even lesser than that. So in general, just to give you an idea, diffusion length is actually 10% of the gate length. This is not a fixed value. It depends on manufacturer to manufacturer, but this is just a rough idea to imagine. So for this 28 nanometer channel length, the actual channel length is actually around 20 to 22 nanometer. So you can imagine this much of channel length. Now, if we are approaching 2023 now, and coming, people are drawing some roadmap for 2030, and it is seen that the Moore's law is no longer valid. So The curve is deviating from the Moore's law. That is, the number of transistors that have been doubled in 18 months is no longer failing. So people are talking about more into sensors and actuators than biosafes, etc. Then you can have more information on technology roadmap for semiconductors and devices. IRDS website, you go and more details you can find here. Now, what is the journey ahead? What will happen after Moore's law? Will the transistor manufacturing will stop because it is not permitting the physics? In reality, it is not so. Yeah. So because of the excessive scaling, there are many other effects. So people are now, for example, working on 2D materials, 3D, terascale integration, all these stuffs people are doing, to compensate the scaling. But for each process, there are some challenges as well. For example, if you use 2D kind of nanomaterials, then heat dissipation is used. Process integration is a problem. Lithography is very complicated. So all this process will in turn will give you, electron tunneling that is not needed. Then 3D terascale integration, 3D integration will give you lots of heat dissipation. So to overcome all these issues, you have to integrate the intelligent sensing, actuation, then data analysis, all these stuffs. Okay. Now let us see the VLSI design flow. So it starts with the design specifications. I have given you some very simple example of an op-amp because all of you probably have studied op-amp in your first year or second year courses. So for example, your company boss will ask you to design some op-amp with some particular specifications with particular value of power, gain, cutoff frequency, common mode rejection ratio, etc., etc. He will give you some specification and you have to come up with the circuit design and the results. So what you will do with after getting the specifications, you will search for some schematics. What kind of circuits? I have shown you some schematic of a low power op-amp. So you will search for some schematics. So most likely that you will not get the exact structure. So you have to design of your own at least some part. Then you have to simulate the structure. So if everything is fine, you are getting the results as expected, then you can go for layout. If you are not getting the results as expected, then you have to go back and again you have to look for another schematic and do some research on the schematic. So then after layout, you have to check the design rule check. That means whether layout on the left hand side I have shown just an example. So if everything is fine, that layout means you have to place all the connectors, then substrates and other materials in proper arrangement. So that is given, for example, 130 nanometer technology. There are some set of rules. According to that rules, those rules you have to place all your connectors, wires, substrates, vias, and everything in proper places. So after layout, you have to check it whether this is fine. Then you have to do the extraction simulation. That means because you have put all the wires and everything in parallel or nearby each other, there may be some coupling of capacitances. You have to check them. So if everything is fine, then so you will send it for fabrication unit. Okay, this is just an example. Now for device research or for semiconductor research, so we are not going to design any circuit for the time being. So what we will do, we'll try to see at the device level. For example, this transistor, we'll see the transistor level. So we'll try to design a transistor that consumes very, very low power, that is very, high speed and all that. So we'll work on the device level. Now, device research is related to material research, device physics, fabrication, nanotechnology, reliability, power electronics, optoelectronics, all these areas device electronics people work. And it is not a it is basically an interdisciplinary area. So many areas of people work here. For example, physics, material science, electrical engineering, all these areas, they work together. Now, what are the challenges? I have mentioned already. The main challenge is people need high power as well as what? Is it high power or low power? Students, do you want a device that consumes very high power or a low power? Dr. Neeraj, you are getting my voice? You can hear me, right?
Yes, sir.
Yeah. So my question was, do you want a device that consumes higher power or lower power?
Sir, lower power.
Lower power, good. So we want a device or electronic gadget that consumes very less power. We want the smartphone, search for a day and use it for 7 days, right? At the same time, we want a very high speed device. Okay, so these are basically the challenges. So to achieve those, or if you want more number of transistors in a chip, or you want more memory space, what you want, you have to reduce the dimensions of these transistors. So for that, you need to do the scaling. Okay, so scaling is a challenge. Material limitations are there. Energy efficiency is there. Heat dissipation is there. Okay, so these are some of the challenges while reducing the dimensions of transistors. Now, when we say low power, we basically mean low power systems. To have low power systems, you need low power circuits, and eventually you must have low power discrete components. When we say low power, again, I am repeating, without sacrificing the ion. Okay, so generally when you get a device with very low power, then on-state current, that means the maximum amount of current that a device gives, that also reduces. So we do not want to sacrifice ion, but at the same time, we want to reduce the ion. This is very difficult, but there are devices we can work with. Also, we want a device with less complexity. You can design some device, this performance is very, very nice, but it's very, very complex to fabricate. Okay, so that will create some unnecessary issues while using the main product. So it is essential that you always look for a product that is less complex. Now, here, if you see the 65 nanometer technology node, then active power and passive power. So both are important, but if you go below 65 nanometer technology, then passive power is even more than the active power, you can see. Okay, so therefore, passive power means what? For example, you are having a circuit or system. In that particular system, at a particular instant of time, it may not be the case that all circuits are used at the same time. So you do not want a particular circuit to operate at that particular instant, right? So can we off that particular circuit for few seconds or few minutes when it is not being used? So if it can be done, lots of power can be saved. Okay, so passive power means the power consumed by the device when it is not in use. Okay. Now, there are two reasons why we want to do scaling. One is to improve the microprocessor speed, and second is to include more number of transistors in the chip. Okay, so these are some of the techniques. At the same time, we want to reduce the voltages, also supply voltage, because power dissipation is the product of supply voltage and current. So if you want to reduce the power, you also need to reduce the supply voltage. For example, I worked on a device that is saturated at 1 volt. Now, if I reduce the power dissipation supply voltage to 0.5, then my power will be half. Then there are different methods to reduce the supply voltages. Okay. Now, let us see how we use these concepts, to design some device-specific system design. Okay. So you start with the foundation in physics. What is there? Quantum mechanics, statistical mechanics, and eventually leading to some transport equations. So these will be useful while designing some devices. For example, resistors, diodes, bipolar junction transistors, MOSFETs, etc. Now, using these devices, you make some circuits. For example, TFT for displays, microprocessors, lasers for hard disk, etc., etc. Now, using these microprocessors and other circuits, you basically design a particular circuit. Now, for us, we will be working on these devices. Okay, so for example, MOSFETs, bipolar junction transistors, etc. So to understand this, what we need the knowledge of quantum mechanics, statistical mechanics, and eventually transport equations. For example, you consider a piece of semiconductor. There you have, a particular doping concentration, let us say 10 to the power 17 per centimeter cube. Okay, so this much of, doping concentration, this much of atoms you have, how many electrons you have in the valence cells. Okay, these electrons will be moving if you apply some potential, right? Now, what is the transport equations? Okay, so that will depend on, that will define the operation of the devices. Now, people started with vacuum tubes in 1947, till 80s it was used, then people use bipolar junction transistors. Then from 1960s or 70s onwards, people are using MOSFETs. So for example, vacuum tubes, what are the problem? Vacuum tubes are bigger in size. Okay, so for example, if you want to make a circuit, you have to use lot many vacuum tubes, and it is very big. And now you consider integrated circuits nowadays, that the performance of your smartphone, you cannot imagine this with your vacuum tubes. Then bipolar junction transistors came. Also, it has some limitations that will come. Then eventually MOSFETs came into play, and till now, until now, it is being used. Now people are trying to use different kinds of MOSFETs and trying to use it for different areas. For example, spintronics, people are looking for biosensors, displays, etc., etc. Now, this figure shows a piece of semiconductor. I have applied a potential, Now, as I have told you, how many electrons will flow depend on these parameters. For example, transport of scattering, quantum mechanics, then the chemical composition of the material, crystal structure, temperature, doping. So these are the parameters, on which the current from one end to the other end of the semiconductor will depend. Now, if we see different types of materials, you have crystalline material where atoms are arranged in a regular and repetitive pattern. Then you have amorphous material, polysilicon material. Okay, so amorphous material is not mostly used, for making devices and all, but amorphous materials are used for bioelectronic devices. So mostly silicon devices are used, which is crystalline in nature. However, polycrystalline is used, while making the gate terminal and all that. Now, The semiconductors are group 4 elements in the periodic table, for example, carbon, silicon, germanium, etc., etc. And silicon is being the most widely used material in the semiconductor industry. So you can have some compounds by combining group 4 elements, group 3 and group 5 elements, then alloys by group 3, group 4 and group 6, like that. So not all combinations are possible. It depends on lattice mismatch, room temperature instability, etc., etc. Now let us start with the device physics. The basic building block is the p-n junction diode. So if we can understand p-n junction diode, then it will be very easy to understand the other devices like bipolar junction transistors and MOSFETs. So p-n junction, if you connect two pieces of semiconductors, one p-type doped and one n-type doped. Doping is addition of impurity atoms to the original atom. Why? Because to increase the current conduction. Okay. So when you have two pieces of semiconductors, one p-type and one n-type, so p-type is positively charged and n-type is negatively charged. So what will happen? For example, I am not connecting any bias from outside. So what will happen? There will be diffusion. Okay. So because electrons are majority carriers in the n side and minority in the p side, similarly, holes are majority in the p side and minority in the n side. So what they will do? They will try to neutralize. For example, electrons in the n side will diffuse through the junction and try to come to the p side. Similarly, holes will try to diffuse and come to n side. Now, when they leave their parent position, then what will happen? They will leave behind some uncovered charges. For example, when an electron leaves its position from n side to p side, they will leave behind a uncovered positive charge. So on the other side also, in the p-type side, when holes leave, they will leave behind some uncovered negative charges. So what you will see? You will see some uncovered charges on both sides of the junction. Okay. So after certain time, what you will feel? That you have some accumulation of charges on both sides of the junction. So uncovered meaning that these charges are not capable of moving. They cannot conduct electricity. However, they can carry the same amount of charge. They have the same amount of charge like holes and electrons. So we know when you have some accumulation of charges, what will happen? There will be some electric field, and because of that, you have some potential. So what will happen? Some potential will be developed around the junction. So that potential wall will stop further movement of electrons and holes on the other side. So this region is called depletion region. Depletion region means depleted means what? Electrons and holes were there earlier, but they have now left behind their original position. So this is called depletion. Okay. And the corresponding voltage is called the depletion voltage. Now, what we have understood till now is because of this depletion voltage, there is no further movement of electrons and holes to the other sides. Fine. Now, if I want some current conduction, so till now there is no current. Okay, so if you see the curve on the right hand side, so this is the portion. Okay, you can see. So this is the portion where there is no current. Now, if you want current, what you will do? Students, please answer. If you still want some current, what you will do? Students. Okay, so you will apply some bias. What kind of bias you will apply? You want the holes to move towards the right hand side, right? So what you will do? You will connect a positive of the battery towards the p side. Why? Because positive of the battery and the positive holes, they will repel each other and they will move towards the right side. Similarly, negative you will connect to the n side so that negative and negative repel and electrons move to the left side. So what will happen? You connect the positive of the battery to the P side, negative of the battery to the N side. So what will happen? This will allow the electrons and holes to cross the barrier and starts further movement, and therefore current starts flowing. Okay, so once the depletion voltage is overcome, there is no barrier, so you have suddenly enormous amount of current, enormous electrons and holes from the both sides will start flowing, and therefore you have an exponential amount of exponential current. Okay, so this is the operation of p-n junction diode. Now, if you see the BJT also same thing. You have two types of structures. One is NPN and another is PNP. So emitter base collector, if you connect the N region to emitter, P region to base, N to collector, we name it as NPN transistor. So how many PN junctions we have? Here also we have two PN junctions. One is between emitter and base, and other is between base and collector. So again, the same thing, you have two depletion regions. So these depletion regions will stop further movement of carriers. So if we want some current, what we will do? So we will apply some bias. What kind of bias we will apply? For example, emitter is negatively charged electrons you have. So you will connect negative of the battery to the emitter, so that negative of the battery and the electrons in the emitter, they repel each other and they move towards the right hand side. Fine. So electrons will flow from emitter to base. Fine. Now in the base region, they will combine with some of the holes, some of the electron hole pair. Okay, and they will be lost. And the remaining electrons will reach the collector region. Once they reach the collector region, they are immediately attracted towards the collector terminal by applying a positive voltage. Okay, so therefore biasing is very easy. You need to understand from which terminal you want to repel the electrons or holes and in which terminal you want to attract them. Okay, that's fine. Now, BJT, what are the issues with BJT? So issues are shrinking the technology as companies try to fulfill the customers' demand. They have to include more number of transistors for more space. Then you have to integrate more number of transistors in a single cell. So BJT has issues with shrinking the technology. Then power dissipation is also an issue. To overcome this, CMOS technology came. CMOS technology means one PMOS transistor and one NMOS transistor. So at a particular instant of time, only one transistor is on. For example, if you give VDD to be positive or higher voltage, only, for example, let us say V input, okay, gate voltage. If you are increasing V input from 0 to 1 volt, say, okay, so if V input is equal to 0, then only PMOS is on and NMOS is off. Similarly, if you give V input to be 1 volt, then NMOS transistor is on and PMOS transistor is off. That means one transistor is on at a time. So therefore, there is no connection between VDD line and VSS line, and there is no leakage current. So this is called zero static power dissipation. For this reason, CMOS technology is chosen. But in reality, it is not so. Power is not exactly zero. There are current, but current amount is very leakage current is very less. Now, the most important device is MOSFET. Okay, so in MOSFET, BJT is a 3-terminal device, emitter, base, and collector. MOSFET is a 4-terminal device. Source, gate, drain, and the fourth terminal is called the buck or substrate. Okay, so in BJT, what we saw, so electrons started flowing from emitter to collector through base. Here also same thing, just names are different. Here in place of emitter, we are using source. In place of collector, we are using drain. And we have another terminal called the gate terminal. So gate terminal is actually controlling the electron flow from source to drain region. Okay. Now this device, okay. So probably I can use paint, so I'm not able to use the whiteboard. Dr. Neeraj.
Yes, sir.
Okay, so you can see my screen, no? You can
Yes,
see
yes, I can see.
my paint screen. Yeah, you can see my screen.
Yes, sir.
Yes.
Okay, okay, great. Okay, so have you studied MOSFET structure, students? I exactly do not know which semester you are in. Okay. Okay, so this is source. This is n-type doped and heavily doped. This is why I am writing n plus, n plus. This is the oxide region and this is the polysilicon region or metal. This is gate. This is p-type substrate and this is called the bulk or substrate region. Okay. Now if you see, this is a metal or polysilicon. This region is oxide region and again this region is semiconductor. So I can write like this. This is a metal. This is a semiconductor. In between I have an oxide. Have you seen this structure, students? This is a parallel plate capacitor. Okay. So your MOSFET is basically a parallel plate capacitor. Now what is the principle of parallel plate capacitor? If I apply some positive charges, the same amount of charge is repelled from the other gate. Or in a sense, I can say that if I apply some positive charges in one of the gates, the same amount of charge is developed on the other plate. So same principle is used in the MOSFET also. So for example, if I apply a negative charge, for example, let us say this is grounded, source is grounded, drain for the time being, let us ground it. Okay. So if I apply some negative charges here, what will happen? You have p-type substrate, that means you have lots of holes. These holes will be attracted towards the surface. So more and more negative charge you give here, then more and more positive charges, these are attracted towards the surface. Okay. Now let us oppose the case. If I apply some positive charges, in the gate terminal, what will happen? You had holes here earlier, so these holes will be repelled from the substrate. When these holes repel, then they will leave behind some immobile charges. They will leave behind some immobile charges. So if you increase positive voltage more, so you have some immobile negative charges. Fine. So you are increasing the gate voltage, and after a certain instant, what will happen? The number of uncovered charges will be more. Now you want electrons to flow from source towards the drain. So in the source region, you have a tank of electrons. Okay. So these electrons are not able to flow. Why? Because electrons flows from lower potential to higher potential. Okay. So as you are increasing the gate voltage, because of this accumulation of charges, there is a voltage, and that voltage is also increasing. Let me name this voltage as Vx. And electrons can only flow when this barrier potential, let me name it as Vb. When this barrier voltage and the voltage that is developed by these immobile charges are equal, then only, or even more, then only electrons flow. That means when Vx is greater than equal to Vb, then electron starts flowing from source towards the drain. So those electrons are free electrons. Okay, so those electrons are free electrons. Okay.
Hello.
So, yes. So now electron starts, flowing from source towards the drain, and these are all free electrons. So earlier I had positive charges.
पहले ये पता अनम्यूट कर कर माइक
Yes.
है साला मेरा
You can hear me, right?
म्यूट करना स्पीकर
You can hear me?
Yes, sir. Yes, sir.
Okay.
Student, you can mute yourself.
पूछ रहा था तुमको क्या तो अभी तो
Students, you can mute yourself.
Okay. So now the electrons that are flowing from source towards the drain are all, free electrons. So electron starts moving from source towards the drain. Okay. Now to increase the number of electrons, what you will do? You will increase the gate voltage. At the same time, you will apply some positive voltage at the drain region. Okay, so you apply some positive voltage in the drain region. So by applying the positive voltage in the drain region, it will attract more of the electrons, and therefore there are more number of electrons flow, and you have appreciable amount of current. Okay. So earlier I had positive charges, now I have negative charges. So therefore it is called channel inversion. That means charges are inverted. So because of application of gate voltage and drain voltage, you can increase the number of carriers in the channel region. Okay. 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 So now you have understood how a MOSFET works. Okay. So it is very easy that your gate terminal is controlling the flow of electrons. Okay. So as if, in a water tap, your tap is controlling the water flow, just like that. So here your gate is controlling the flow of electrons from source towards the drain region. There are many other issues. So we are talking about a long channel MOSFET. If the length of the channel reduces, then there are many effects that comes into play. Those are called short channel effects. Probably sometime later we'll discuss. And these are some of the curves. This is called the transfer characteristics, ID versus gate voltage, and this is ID versus VDS. Okay, this is fine. Now what I want to show you, there are different types of devices. Okay, these are all conventional MOSFETs that we have discussed, but the amount of current or the amount of the electrostatics behavior, these are not sufficient to have very high performance devices in smartphones and other devices that you are working. So people are doing some research or trying some new devices every day so that they can find a good performer. Okay. So people look for, this is the buck MOSFET that we have just now discussed. People look for, SY MOSFET. Then instead of one gate that I have shown you, people use double gate. That means 2 gates, 3 gates, or gates all around the structure. Then tunnel FET for extremely low power applications. Then carbon nanotubes, graphene, single electron transistors, etc., etc. All of these devices have some pros and cons. Okay, none of these devices are good in all specs. Some parameters are good, some are bad. And some of the techniques that are being used to improve the performance in a MOSFET are, for example, channel engineering. So here we use different types of materials. For example, we use silicon, germanium, combination of silicon and germanium. Then we use strain silicon. We strain the silicon so that collisions are less, so mobility can be improved. Then we dope the silicon region, okay, so that we can improve the device performance. Then another technique is called gate engineering. That means we can change the work functions, different types of work functions, different function materials to improve the device performance. Then oxide engineering. So instead of silicon dioxide or commonly used oxides, if we use high K oxide materials, zirconium oxide or something like that, then you can actually improve the device performance. Now here some of the simulators you can use. In fact, if you do not have your licensed version of simulator, still you can work in semiconductor research. There are some free softwares at nanohub.org that is from Purdue University. Then for device simulations, you can use Synopsys Syntoras TCAD. Then you can use Silvaco TCAD. We have licensed version for Syntoras now. Then you can use SPICE for circuit simulation. LT SPICE is free. Other SPICE softwares are also there. LT SPICE is quite good. Probably you can use 30 transistors. For analog circuits is quite good enough. Cadence, Mentor graphics, these are all used for front end as well as back end. For packaging, you have different types of packaging as well as mechanical behavior of structures. You can use COMSOL multiphysics, you can use ANSYS, etc. So these are some of the steps for fabricating the MOSFET. Now next, I want to show you how a MOSFET that is different than a conventional MOSFET can be used for a better performance. So one type of MOSFET is called junctionless transistors. So earlier, the MOSFET that we discussed just now have 2 p-n junctions. Okay, so this is one p-n junction between source and channel, and other p-n junction is between channel and drain region. Can we have a transistor that is without the p-n junction? So answer is yes. So here you have, earlier we used heavily doped source region and drain region, and channel region was lightly doped or no doped. Now here both source gate and source channel and drain region are very highly doped, and both of them and all the regions are n plus n plus n plus. If it is a n-type MOSFET, the whole region is doped with n-type material. If it is p-type MOSFET, whole region is doped with p-type material. So earlier for n-type MOSFET, conventional MOSFET, if it is a n-type MOSFET, we used n-type polysilicon gate. N-type polysilicon gate means work function of around 4.5 or something like that, or below 5 electron volt, we say n-type polysilicon. So if it is more than 5 electron volt, we say it is p-type, p plus polysilicon gate. So in junctionless transistors, we use p plus polysilicon gate. The whole region is highly doped, and therefore the flat band voltage is very high, 1.1 electron volt. Now, what are the advantages of this device? Advantage of this device is better short channel effect performance. The main issue with the conventional device was the short channel effect. So if you reduce the channel length, then second order effects came into play. So with this kind of device, we can actually improve the short channel performance. So if short channel performance is improved, electrostatics is improved, then we can have very good standby power operation. So these devices offer a very low power operation. Okay. So again, I said, you cannot have a free lunch, so you have to pay for it. So you are getting better electrostatics, but the drain current of this device is not that great as conventional transistors. So on current is somewhat lesser than the conventional transistors, even though off current is better. So however, we are more interested for ion by IF ratio. Ion by IF will tell you how fast you can operate the device. So ion by IF for this device is very good. So therefore you can have fast operation. Okay. I will skip this with the interest of time. And another example just I want to show you is wide bandgap semiconductors. Okay, so the silicon is not wide bandgap semiconductor. So wide bandgap semiconductors are very useful for high temperature applications and for extreme environment applications. For example, if you want to design some circuit, those are useful for aircrafts and all that. So where extreme temperatures the device has to face. So in those cases, we may not use silicon. So in those cases, we may have to use some devices with a very high bandgap. So silicon carbide is one type of material that is useful for such kind of devices. For high temperature applications, we use this kind of devices. This is just to tell you that for different applications, for example, if you want to reduce the power, you use certain kind of device. If you want to use for example, reliability purposes, for example, if you want to have a good device for better temperature performance, then you use a different kind of device. Now, this is a slide that I want to say you that when you do or study something in semiconductors or in devices, so while doing simulations, you just blindly cannot simulate. You have to verify your simulation with existing fabricated devices, or at least with some simulation devices where fabrication is not already reported, with very good journal like IEEE standards or something like that. You have to first calibrate your device, then only this is acceptable. These are some of the results for, I used silicon carbide based transistor for high temperature applications. These are some of the results. And also you can do some circuits. So you can extract some of the parameters in your device simulation, and you can use those extracted parameters and you can integrate it in your SPICE simulator. So basically you can design some circuits by using your own devices. Okay, so by using different kinds of methods. So lookup table is one of the method. Here I have designed a boost converter by using the wide bandgap semiconductor device that I used using silicon carbide. Okay, so yes, for books in this area, you can go through this space. I have mentioned lots of good books. You can find them, and now you can see the opportunities in semiconductor research. Or if you are looking for jobs, there are so many areas you can look for jobs in semiconductor research, like research and development positions, process development, device physics. If you are good in mathematics, there is a scope for you. Then material science, quality and reliability. Okay, if you are good in coding, then also you have positions. So every area that you work with, starting from signal processing to biomedical, every area is covered in semiconductor research. Everybody has a scope in this area. Now, another important question students often ask is, okay, what I need to do to get a job in this area? So to get a good job, you need to have a, master's in this area, semiconductor or circuit area, or PhD in physics, electrical engineering, etc., etc. Nevertheless, the most important question is, can BTech students get a job in semiconductor industry? Answer is yes. In all these areas, for example, process engineers, test engineers, front end, back end, in every aspect, so you can find a position even after doing a BTech. Now, how to find a job in these areas? You can go for LinkedIn profiles. So many companies, or many people you can connect through LinkedIn. You can search for naukri.com, Monster, Semiconductor Today Jobs, semiconductorjobs.in, etc., etc. IEEE job sites you can search. Now, if someone is interested for PhDs, you can directly go to a PhD. Now, if you have 75%, then you can directly do a PhD in IITs, in IIScs, or any higher institutions in India and abroad. There are good fellowships now. For PhDs, people will get around 37,000 as JRF and 40 plus after 2 years, that is SRF. Okay, and there are some even better fellowships like Prime Minister's Fellowship, like that. Okay, now if you want to find a PhD in India and abroad, findaphd.com. Then you go to their websites, academic jobs online. There are many sites you can go, and I'm sure you can find a job or higher studies opportunities in this area. So I think this is fine for my side. So it's 4. Yeah, Dr. Neeraj, I can take few questions if any.
Yes, yes, sure, sir. Students, do you have any questions? Raise your hands. Okay, sir, I want to ask one small
Yeah,
question
sure,
from my
sure.
side.
Yeah,
Nowadays, artificial intelligence is integrated with the semiconductor devices.
yes.
So how you think about that artificial intelligence is useful for us in the semiconductor domain?
Yes. See, nowadays what is happening, artificial intelligence is tremendously used. Okay, so let me give an example that will be very nice to understand. Okay, for example, in the tea industry, okay, so what artificial intelligence is doing, for example, I want to taste tea, whether your tea is good or bad. Okay, so for the already branded teas, okay, I can say that, okay, this brand is good or this brand is bad, or etc., etc. Now, for the gardens who are very new, for example, 2 years back or 4 years back, they started and they started plucking leaves this year. So we do not know their quality. So how to judge their quality? So for that, artificial intelligence is used. What people are doing? So from the known gardens, they collected some tea leaves. For example, 10 different gardens, they collected 10 different types of tea leaves, and they have graded them accordingly. For example, this garden tea is very nice. They have graded 10 out of 10, or somebody is lesser performance, 9 out of 10, or 6 out of 10, like that. So they have extracted some parameters that, for example, for 10 grade tea, these are the parameters you need to achieve. For accordingly, for 5 grade, so these are the parameters of the tea, and they have saved it somewhere, some system. Okay, now they have enormous amount of such kinds of data like that. Now, when a leaf from new tea garden comes, okay, with these parameters, okay, these are the parameters for the new tea garden. Okay, they will compare with the already existing data. Okay, so these data are coinciding with this grade of tea. Accordingly, this garden will be graded. So these type of applications are already being started in the even in the local markets also. These are being started. So we have also started a work something like this. We have sent one proposal connecting with the tea industry. Now electronics are being used for the local needs of the people, so we must do that, and this is one of the example. Dr. Neeraj.
Thank you, sir.
Yeah.
Any other questions, students, you want to ask?
So, like, if we are the students from the EC department, can we connect to sir after this year if we want to?
Sorry.
Ans, can you repeat your question? Ans Pathak.
Sir, yes, sir, I was asking it, like, I am from the EC department, EC background, and like I will require some help and some guidance from the sir in the coming years. So can we connect to
Oh,
sir in
yes.
the future?
I'm always available. My email ID is there in the slide. Okay, so you can connect me anytime, and Dr. Neeraj is there. Through him also you can connect me. I'm available anytime, no problem. Any guidance.
And sir, can we get this PPT that you are teaching with? Can we? Because I have joined a little late because my internet connectivity was very poor at the beginning, and I joined
Okay.
when you were
Yeah.
approximately near 45.
Okay,
So I missed the
sure.
45.
Maybe I can give the slides. Okay. There are some slides related to my work. I will remove those, and rest I can give you. No problem. Okay.
Thank you so much, sir.
Okay.
So, any other questions, students? Can we end the session?
Yeah. So if there are no questions, then probably we can end.
So, thank you very much, sir, for your wonderful insight into the semiconductor domain. You have given the overview of the MOSFET, which is the basic for the all EC students. They must know it. Then you highlight the recent devices, that is junctionless MOSFET. And after that, you have shown us the wide gap semiconductor materials. So that is definitely beneficial for our students. So on the behalf of EC department, MIT University, Haryana, I thank you, sir. Thank you very much, sir. Now I request the participant to turn on their camera so that we can have a group photograph.
Okay. Thank you. Thank you so much, Dr. Neeraj, for your invitation. Okay. So we can definitely have more talks in future. Okay. Thank you so much.
Sure, sir. Participant, please turn on the camera for the group photograph. So thank you all. Thank you very much.
Okay. Thank you so much. Yeah. Thank you.
Thank you, sir.